Swayam Prabha. Digital India. Educated India.
All right, so good morning, good afternoon. Welcome back to our series of courses on analysis and design of rigid pavements. So in this class, we are currently on module 4, which is the main part of the course, the part of the course that we are actually interested in, which is the mechanistic empirical design of rigid pavements. But just a quick recap of what we've been doing in this class. So module 1 was more of an introduction. In module 1, we learned that there are 4 different types of rigid pavements. That is jointed plain concrete pavements, JPCP, jointed reinforced concrete pavements, JRCP, continuously reinforced concrete pavements, CRC, and pre-stressed concrete pavements, PCP. Now, we learned that JRCP and PCP are fairly specialized applications. In fact, JRCP is very rare today. So, we are not really going to talk about those two applications. JPCP is by far the most common type of rigid pavement. So, at least it might seem up to this point, a vast majority of this class is devoted to JPCP. CRCP is not as common as JPCP. It's certainly much more expensive than JPCP. But CRCP is the analysis of CRCP actually closely tracks the analysis of JPCP. It's only at the point of their design that they start to diverge. So, although we've been studying analysis of JPCP for most of the class, rest assured that we've also been studying CRCP more or less along the way. Now, that was module 1. Module 2 was the analysis of rigid pavements, and actually both module 2 and module 3 were analysis of rigid pavements. Module 2 was the so-called classical methods for analysis. Classical methods meaning old methods, methods which are actually starting from Westergaard, about 100 years old at this point. And those are methods where you, at the end of the day, making a number of assumptions, some valid, some not so valid, making a number of assumptions, they came out with some simple formulas, closed form solutions, closed form equations that you could calculate by hand if you wanted to. You could plug it into a calculator. You might use it on a spreadsheet. But there was no need to do any sophisticated computer programming or sophisticated mathematical analysis to get the solutions. In that category, we saw Westergaard's equations. We saw some modified versions of Westergaard solutions. We came across Freiberg theory. And all of these we saw were built on top of a very celebrated differential equation, which was the Sophie-Germain equation. Now, at the end of module 2, we also came across the fact that there are certain limitations to these analytical solutions. What are those limitations? So, for example, perhaps the biggest assumption the analytical solution makes is a so-called infinite slab assumption. That is, wherever the load is placed, whether it's placed in the interior, whether it's placed on the edge, whether it's placed on the corner of the slab, regardless of where it's placed, the slab is very large. That is, any joints which are not immediately close to the slab are assumed to be very far away from the slab, and therefore they don't have much of an effect on the stresses and displacements developed in the slab. That's a major assumption because, as we saw in practice, rigid pavements are typically 3.5 to 4.5 meters in width. That is not an infinite pavement. That is a pavement which is finite, where the joints do have an effect on the stresses developed. So that is a very major assumption that these analytical solutions make. There are other assumptions. Analytical solutions assume that the load has a circular footprint, and we saw that some solutions did allow also for a square footprint, but that was more or less it. Other assumptions, analytical solutions make the assumption of a tension spring. So we know that for JPCP, we basically analyze JPCP as a slab sitting on top of a bed of springs, what we call the Winkler foundation. So that's a Winkler foundation assumption for the subgrade. So what the analytical solutions assume is, if the slab is pushing downwards onto the subgrade is providing some type of reaction. That's fine. They also assume in the other way that if the slab is moving upwards, that is, the slab is moving away from the soil, then the soil is actually pulling the slab back. In other words, the soil is able to tolerate tension. It's able to resist tension. That is obviously not realistic. You can go outside and try. Put your foot on the ground and press on the ground. You'll feel a reaction. Now lift your foot off the ground. The ground is not going to pull you back. And so that is a major assumption which goes into the analysis of rigid pavements. It is for these reasons that over the last 30 years or so, and this is what we saw in module 3, over the last 30 years or so, the analysis of rigid pavements has moved away from Westergaard's solution and has now gone into using the finite element method, or in more general terms, numerical methods. Now, we saw the basis of these numerical methods was, first and foremost, as a philosophical basis, we give up the idea that we are going to get an exact solution. We are willing to tolerate some error. And as we talked about, the reason we are willing to tolerate this error is because in practice, that is in construction, we do have some amount of errors. So whatever we design on paper, the exact same thing is not going to appear on the field. On the field, you're going to have some variability. So it's fine if our analysis also has a little bit of variability. And a little bit, I mean maybe around 1%, at most perhaps 5%, but generally 1% of the analytical solution. So first of all, in the finite element method, we learned that we are willing to tolerate some amount of error. Secondly, we learned that in the finite element method, we will not actually be solving the solution at every point. Instead, we discretize the slab or system of slabs. We discretize the slab into certain points which are called nodes. The nodes themselves are connected using what are called elements. And of course, the whole slab is divided into a finite number of elements, hence the name the finite element method. So these nodes, in each of the nodes, we end up solving for 3 values. There are actually different ways to do it, but the way we learned it using a certain assumption, certain sort of finite element modeling, at each node we solve for the displacement and 2 rotations. That is the rotation on the x-axis and the y-axis, and the displacement in the direction of the z-axis. So we solve for those 3 variables at each node. When we solve for those 3 variables at each node, they are called the degrees of freedom per node. At each node, we solve for the degrees of freedom. And this is the main assumption in the finite element method. In between those nodes, that is somewhere within an element but not at a node, we assume that the solution, that is the displacement and the rotations, are some sort of interpolation. It need not be linear, it could be a different type of interpolation. They are some sort of interpolation function of the values at the nodes. That is, if I know the degrees of freedom at the nodes, I perform some type of simple interpolation in order to get the value at some point inside an element. This is obviously an assumption. That's not actually what our real solution looks like. But if we have a sufficiently fine mesh, that is, if we have a sufficient but finite number of elements, we assume that our solution is eventually going to converge. In other words, as the number of elements tends to infinity, it will never be infinity, it will be a finite number. But as the number of elements tends to infinity, the error tends to 0. That's a very fundamental assumption of the finite element method. Now, as we also saw the application of finite element method for analysis of dowels. We saw the dowel component bar model, for example, which is what is used in a modern programs for jointed plane concrete pavements. Now, after all this, what we realized was, at the end of the day, what the finite element method really does, we have a differential equation, a partial differential equation. The partial differential equation, solving it analytically under a set of boundary conditions, etc., is very hard. And in many cases, it's not possible. What the finite element method does actually is, it converts the partial differential equation. So one partial differential equation is converted into a series of algebraic equations. And when I say series of algebraic equations, it is not actually, well, conceptually it's similar to what you learned in high school, but it's not really the same, because what we get is, we don't get 2 or 3 equations. We get thousands, tens of thousands, hundreds of thousands of equations which have to be solved. Obviously, you're not going to solve hundreds of thousands of equations by hand, and neither do you have to. What happens in practice is that we have a computer program to solve it. Either we write the program ourselves, or today there are actually many programs, commercial and open source, which are available. Many of them general purpose, that is, they're used in a variety of fields of engineering, and some, like we saw in at the end of module 3, ISLAB 2000 or ISLAB 2005, which are specialized programs designed to analyze rigid pavements in particular. Now, the advantage of having these sort of programs is, or using the finite element method, yes, we are incurring some solution, but now we overcome almost all the assumptions made previously. So when you use this finite element method, you do not have to assume an infinite size slab. In theory, the shape of the load can be any particular shape that you want. You can assume tensionless springs, etc. So there are many assumptions which are made in these analytical solutions, which can be overcome using the finite element method, but yes, at the cost of some amount of approximation in the solution. Another advantage of using the finite element method is because it's computer friendly, we can actually package it very nicely within a computer program. So you don't even have to know anything really, although it's always good to know about the finite element method. But truly speaking, you don't really have to know too many details in order to run an analysis. Okay, so that was module 3. We have been on module 4 so far. So in module up to module 3, we learned a lot about analysis. In module 4, what I told you was that design, or mechanistic empirical design in particular, which we'll go into more details about today, design is actually an iterative analysis. That is, in design, generally we choose some kind of a trial section. From the trial section, we run an analysis and calculate maybe stress or maybe displacement, but some sort of mechanistic output. And then we compare that to some sort of limit, and if our value is below our maximum limit, whatever that limit is, then we call that a successful or a pass solution. If it's not, then that's a failed trial solution. We go back, update our trial solution, and keep going forward. So the reason we spent about half the class really learning about analysis of rigid pavements is because design is basically a iterative analysis. So we had to have very good hold on analysis before we actually went into design. Now, what we've studied so far in module 4, which is on mechanistic empirical design, first of all, I explained the concept of mechanistic empirical. So what we learned is that, first of all, rigid pavements are not designed as we would design structural members. Structural members, at least in India today, are designed using what is called the LRFT concept, limit and resistance factor design, load and resistance factor design, sorry. So in that, what we assume is that we have some kind of we have some loads which are factored, that is, we put some factor of safety on them. So we have some factored loads which generate a stress and a displacement, and then we have some kind of a factored resistance factor, a factored resistance, and that is some measure of strength, or it can be some measure of the maximum amount of deflection which is allowed. So we have factored load, we have factored resistance. If factored load is less than factored resistance, the design has passed. What we saw is, if we use LRFT design in JPCP or for rigid pavements in general, what we find is that our designs always pass. As we saw in some previous examples, our stresses are always less than strains. In fact, for a properly designed rigid pavement, the stresses are much less than strains, than the allowable stresses. So in that case, can we use LRFT design? No. So what can we use to analyze rigid pavements? In the previous lecture, we went through the concept of fatigue theory. Fatigue theory says that when you apply a load onto a structure such that the stresses developed are much less than the maximum allowable stresses, even then a small amount of what we call damage takes place. That damage is in the form of micro cracks. So we may have a structure, for example, you may load it very lightly, but you'll have a little bit of micro cracks forming throughout the structure. As you keep loading cyclically, that is, you don't just apply one load, but you keep applying, unapplying, applying, unapplying, so on, hundreds of thousands of times, you keep cyclically applying a load, then these little micro cracks which are forming will eventually start coalescing and coming together into one large macro crack. And that is a point that we could call failure. So the theory of analyzing this sort of a failure mode, where failure is not occurring because of one application of a load, but it's occurring due to multiple applications of small loads, this theory is called fatigue theory. So we learned that in fatigue theory, at the end of the day, we are interested in a particular value called fatigue damage. This comes by calculating stresses and then converting the stresses into a certain number of allowable stresses using what are called SN curves. We saw what SN curves are. We also learned the concept of endurance limit. That is, below a certain stress level, you can have an infinite number of repetitions and you will not have this crack which is coalescing. And that value we called as the endurance limit. And finally, we also looked at the concept of transfer functions, where a transfer function was basically a way by which we calculate fatigue damage. So calculation of fatigue damage is a purely mechanistic process. You calculate stresses, you take an SN curve, and an SN curve is sort of a constitutive model in the sense of fatigue theory. So you take the SN curve and you calculate the allowable number of repetitions, and then you take the actual number of repetitions N divided by the allowable number of repetitions NF, and this is what we call fatigue damage. You can sum that up over all loads and all climate conditions, and you'll get the cumulative fatigue damage. And one application is, you could say, failure occurs when the cumulative fatigue damage just reaches 1. So that is at CFD is equal to 1.0, that is when failure occurs. That's one approach. That's a mechanistic approach of failure. There is another approach in which we relate the fatigue damage to some distress that we are interested in. So what are the distresses that we're interested in for JPCP? We learned about this at the end of module 1. We had transverse cracking. Sometimes we have longitudinal cracking. We are interested in faulting. For CRCP, we are interested in, for example, punch outs. We are also interested in the width of the cracks. So really, as pavement engineers, these are the numbers we're interested in. Fatigue damage is more of a mathematical concept. It doesn't truly mean anything as far as engineering is concerned. But cracking, faulting, punch outs, these definitely mean quite a lot. So a transfer function is an empirical function. I underline that fact. It's an empirical function which takes fatigue damage, which is a mechanistic value, and converts it into a distress. So it's an empirical function which takes fatigue damage and transfers it to some distress. And that's what we call a transfer function. That is actually the second half of the term mechanistic empirical design. So the mechanistic design is up to the point of calculating fatigue damage, and the empirical design is going from fatigue damage to some type of distress. Hence, mechanistic empirical design. Okay, so at this point, all of you are now well versed with what is mechanistic empirical design, what is the philosophy of ME design, why do we need ME design. Well, philosophy and all is good, but at the end of the day, since we are all engineers, we want to be able to actually perform a design. So we have to know what are some major design guides in the world. And that's why in today's lecture, after that pretty long introduction, today's lecture is based on the overview of what is the AASHTO MEPDG, the Mechanistic Empirical Pavement Design Guide. We'll talk more about this. This is actually the US and a little bit in North America in general, but this is the US design guide, and it is probably the most sophisticated mechanistic empirical design guide across the world. Now, I will also be talking about the Indian guide in a couple of lectures. That in India, we use another code of practice, which we call IRC 58. So I will talk about that in a couple of lectures, but there is a lot of overlap between the two. So as we are learning about AASHTO MEPDG, understand that a lot of the concepts will also be reapplied when we study IRC 58. But I wanted to take you through MEPDG because it is more sophisticated. It has many more variables and many more intricacies than IRC 58 and many other design codes around the world. So that's why I wanted to start by talking about this. Okay, so today what we are going to do, the agenda for today's lecture is, I'm going to explain the history of AASHTO pavement design. I'll tell you what AASHTO is also. I will describe the process of the AASHTO MEPDG, the Mechanistic Empirical Pavement Design Guide. Now, by the way, one little note, the MEPDG also has another name. It was rebranded, so to say, a few years ago into what was called Pavement ME. So that is Pavement Mechanistic Empirical. So it's sort of a brand name, AASHTO Pavement ME. When I learned this topic, it was called MEPDG. A little bit after I learned the topic, they changed the name to Pavement ME. So out of habit, I'm going to use these two names almost interchangeably. So sometimes you'll hear me say MEPDG, sometimes you'll hear me say Pavement ME. Understand that more or less they are the same thing. I'm referring to the same idea. And finally, I'll also introduce you the concept of level 1, level 2 and level 3 design, which will give us an interesting insight to certain aspects of design, which might not be obvious, although I've tried to explain it in preceding lectures. But it might not be obvious, but it will fully explain certain issues that we have when we come across design, which are not issues that we have when we do analysis. Okay, so let's first start with talking a little bit about pavement engineering. So I titled these A Brief History of Pavement Engineering after a very famous book in physics, paraphrasing from there. Okay, so in historic times, that is maybe 2000, 3000 years ago, roads were built extensively. You find long, pretty good quality roads relative to the sort of traffic that was expected. but you find long and pretty good quality roads in India, in China, in Rome. Indeed, there is the ancient Silk Road, which was not one road, it was actually a series of different paths going right from China, crossing through India, through Kashmir, and then going all the way to Europe, where trade and goods and people flowed. So roads were built extensively in historic times. It's not a new idea to build roads. In fact, one could argue that road construction or building roads is what kicked off civilization in practice, because that's how you could move goods from one place to another, after agriculture, of course. The problem was, in those historic times, roads were not really built using scientific principles. The idea of using the scientific method, that is, you create a hypothesis, you test your hypothesis, you see whether you're actually getting the solution you expect, and you update your hypothesis, etc. These scientific techniques which we use, they weren't really there at that point of time. Now, coming much closer, so going from a couple of thousand years ago to around 100 years ago, before World War II, also there were a lot of roads. In fact, at one point of time, the East India Company, they started a public works department in India to actually construct a large number of gravel roads, linking, for example, Calcutta to Peshawar through Delhi, and there were several other roads as well. But the key was that pre-World War II, road design or road engineering was not considered a formal field of study. It was understood that it could be done and it should be done, but it was done largely based on experience. That is, what people tried in the past, what they knew worked, what they knew didn't work. Based on that, they would collect their experience and they would build roads. Now, in World War II, things changed rapidly. Because of the exigencies of World War II, there was a need to build a very large number of roads very quickly. A lot of people, a lot of equipment had to be moved very quickly. It was quite literally a matter of life and death. And so there was a rapid acceleration of road construction during and just a little bit, a couple of years before World War II formally began. But again, here it was based on very limited data. So although a lot of expansion happened and some scientific principles to some extent was used, it was still based on very limited amount of data, because there's only so much data that you can collect during war. There was a need to finish work as soon as possible. Now, after the end of World War II, going up to around the end of the 1960s, was the era of the road tests in India. And I'll explain these road tests a little, but they were, as the name suggests, they were some roads which were constructed on which some testing was done. And I'll explain what that testing was. So there was the Maryland road test, there was the Washer road test, there was the most celebrated one, which we'll talk more about in detail today, was the AASHTO road test. And I know it's AASHTO when I said AASHTO before. I'll explain the difference in a couple of slides. The concept of road tests still goes on today, largely in the US, but there are other places in the world also, including in India. So the concept of road test goes on. Perhaps the largest type of road testing, although it's not really testing anymore, it's more monitoring. The largest testing or monitoring program in the world today is also in the US, what is called the LTPP data monitoring program. I'll define LTPP. This is the long-term pavement, I'm just shortening pavement as PAVT, Pavement Performance Program. So the long-term pavement performance program, or the LTPP data monitoring program, is a program in the US where basically they have several roads all across their country which they're monitoring regularly. So what does monitoring mean? They have sensors which are measuring perhaps temperature, they're perhaps measuring stress. They are going regularly and collecting what type of distresses are collected. There are loop detectors and instruments which are measuring traffic. Some of them have weather stations nearby where the kind of climate conditions are being measured. So those are active roadways, they're not test sections. They are active roadways which nonetheless are being monitored very closely. And what is interesting, which I will actually show you a little bit in a couple of lectures, what is interesting is all this data is freely available online. So even in India, I've seen a lot of research being conducted where a lot of validation is done using this LTPP database. So it's really a remarkable database which is available to everybody around the world, where you can really see how pavements are performing and run a lot of scientific tests and a lot of scientific experiments using that data. Okay. So as I said, in ancient times and before World War II, pavement engineering was based on experience. It was engineering, it was not too much of science. From the 1950s to the 1990s, however, starting with those road tests, the AASHTO road test, the Washer road test, the Maryland road test, starting with those road tests and all the large amount of data that was collected from them, new design standards. So now the idea of creating design guides came up. So let me write that word over here. The idea of creating design guides, or sometimes in India what we call design codes or codes of practice. The idea of generating these came up. The idea here was collect all the experience, collect all the data which has been collected in these tests, and come up with scientific principles on how to design roads for various conditions. I say roads, but what I mean exactly here is rigid pavements, although this equally applied to the history of flexible pavements. So in the 1950s to the 1990s, several design guides came up all over the world, including in India, and they are based on empirical relationships. Recall what we talked about empirical. So an empirical relationship might mean that you measure a value of X, you measure some output Y, which is X is the independent variable, Y is the dependent variable, plot them together, and maybe you can fit a line through it. There are more sophisticated methods to do it, but in principle, this is what an empirical method is. So many empirical relationships were developed and empirical methods were developed from these road tests, especially the AASHTO road test. It was the most widely constructed, the most intensive road test which was conducted, and indeed going all the way till the 1990s, and in India actually even into the 2000s, most road design manuals in the world were based in one way or the other on the AASHTO road test. Okay, so from the 1950s to 1990s, the pavement engineering truly became a scientific concept, but it was a scientific concept which was based on empirical relationships derived from those road tests. We still had not brought in the idea of using physics to guide the design of pavements and rigid pavements in particular. So from the 1990s to the present, that's where this particular change started happening. The concept, the philosophy of pavement design, if you may, from the 1990s onwards, was based on scientific principles of mechanics of materials. Mechanics of materials, for those of you who have a civil engineering background, this term should be ringing a bell because you might have taken a class. Sometimes it's called mechanics of materials, sometimes it's called strength of materials, sometimes it's called solid mechanics. Different words, same concept. That is, ultimately goes down to calculating stresses and strains for a given body. So from the original time when we just had empirical relationships, that if we knew certain properties of the, say the subgrade, if we knew certain properties of traffic, then we plug it into some kind of formula. It might not be a simple formula. It might have to be an iterative formula, for example, but we plug it into a formula and then out comes the thickness. From there, we've gone today to the idea of using these mechanistic models, which is what we've actually learned in module 2 and module 3. Using these mechanistic models and using them then to design rigid pavements. So from the 1990s onwards, that has been the ongoing philosophy. Okay, so I've given you two terms over here, AASHTO and AASHTO. Let me formally tell you what these two are. So these are both organizations. They are sort of quasi-governmental organizations. I'll explain why I say that in a second. So AASHTO, which was that celebrated road test, the American Association of State Highway Officials. So this was established in 1914. That's actually when World War I started, although the US had formally joined World War I at that time. So it was established in 1914 as a quasi-government body to set standards for highways in the US. That was the time when highway design was just starting to pick up in the United States. Why do I say quasi-government body? It's not actually a formal government body. And this, by the way, is also how the road design standards in India work. You have you have an association of officials who are responsible, and those are government officials who are responsible for the design, maintenance, construction of highways. Those officials have come together into a sort of non-official body, a non-government body. And that body is not tasked with designing or building roads. The actual work of designing and building and maintaining, those are still controlled by the government. This body is a standard setting body. It's a body which is looking at scientific principles, conducting experiments, funding experiments, and then based on that, coming up with guidelines. Those guidelines can be used by governments, but the body setting those guidelines is not actually a part of the government. So that's why it's called a quasi-government body. In India, as we will learn in a couple of lectures, we actually have a similar setup where an organization called IRC, the Indian Roads Congress, which is actually older than India has been independent. The Indian Roads Congress is also a quasi-government body which sets standards, but it's not a body that actually builds roads. The officials in India, the government agencies in India use IRC standards, but IRC itself is not a government organization. So similarly with AASHTO. Now, over a couple of decades after 1914, AASHTO actually changed its name from the American Association of State Highway Officials. It became the American Association of State Highway and Transportation Officials. The idea being that it should not focus exclusively on highways, but also look at some other multimodal fields of transportation. Nonetheless, mostly they do still look at highways. So this is the logo which I've put over here. So that is basically what AASHTO is today. It is a quasi-governmental body which consists of government officials whose mandate is to set standards in the US for the design, maintenance, construction of highways. They set the standards, they don't actually do the work. Okay, as I had mentioned, the AASHTO, which is now AASHTO, in the 1950s onwards, they actually conducted a large number of road tests. So from 1956 to, this should be 1960 approximately. So from 1956 to 1960, in a little place called Ottawa, Illinois, USA, I've actually had the pleasure of being there earlier. So it's a very small town. I mean, compared to an Indian town, not even a city, compared to an Indian town, it's a really small town in terms of population. But just outside this very little town, they basically got a parcel of land and they constructed what I have in this figure, these test loops. So there were two test loops over there. So what is a test loop? Well, it's a road which is a loop. So as you see over here, the road, if it starts from here, traffic would go around and loop and come back to the same point. So it were these two loops, and within the loops then they were divided into several test sections. So maybe on one section you have a JPCP which is maybe 200 mm thick. Next section you'll have JPCP which is 400 mm thick. Similarly, in some cases you'll have JPCP which is maybe M40 concrete, another one where you might have M45, M50 and so on. So a large number of test sections by varying different properties were constructed along these two test loops. And for all of these years, 1956 to 1960, that's 4 years, almost continuously, day and night, traffic was going around. So they had these heavy trucks, heavy by that time. Today our trucks are much heavier than what was there in 1950, 1960. But a large number of heavy trucks were brought. They were taken around this track continuously. Basically, until they ran out of fuel, they would come in and they would just keep looping around the track. The track itself was instrumented in the sense that they weren't electronics back then, 1950-60. So they were instrumented in the sense that a lot of measurements were being taken during this process. So the measurements were, for example, the amount of cracking, the amount of rutting also, because the AASHTO road test also included flexible pavements. So the amount of cracking, the amount of faulting, the amount of pumping, all of these were measured. Furthermore, climate was sort of considered in the sense that you had this location, Ottawa, Illinois. Whatever weather you could measure during the test period, that weather was measured. Now, I should tell you, for those of you not familiar, this place, Ottawa, Illinois, is a really cold place. Winter especially there can be quite brutal. Summers there are hot, but they're not the equivalent of, say, more tropical parts of the world like India, where it's significantly hotter. So this was not particularly a representative climate for the entire world, or indeed even for the entire US for that matter. So some climate data was collected, but really it was just for one location. So very, very limited consideration of climate. So these test loops were subjected to various tests, as I mentioned. So you had different types of roads constructed at a couple of hundreds of meters all along these test loops. As you can imagine, if you're going to drive vehicles almost day and night for 4 years, you're going to collect a very large amount of data. So a huge amount of data was collected. And this then went on to form a design standard in the US initially, because that was the idea. But actually, this data was so large and so voluminous that most other countries in the world, either they directly adopted the same standards, or like India, we use that as a starting point to derive our own standards. So the AASHTO road test is really a historic moment in pavement engineering, because it set the basis for the design of standards, not just in the US, but actually around the world, including to a very large extent in India also. Okay, but sticking to the history of AASHTO and its design guides, so based on the AASHTO road test, the testing of course ended from 1956 to 1960. The very next year in 1961 came a particular manual, which was the AASHTO interim guide for the design of flexible pavement structures. Note, flexible pavement structures. So they were interested at that point largely with flexible pavements. There were rigid pavements at that point, but at least in the beginning, in 1961, the AASHTO road test didn't really develop a design standard for rigid pavements. Now, in 1961, you had that edition. The very next year, 1962, introduced some more modifications, which included some design methods for rigid pavements as well. So the rigid pavements came a little bit after the flexible pavements. 1972 and 1981, further revisions came out for the interim guide. The 1981 revision actually did not make any revision to the flexible pavement, and the flexible pavement part was the largest part of the design guide. So the 1981 revision did not make any revisions or any significant revisions to flexible pavements. There was actually what I wrote here is minor revision because it was a very small number of pages, but actually it was a pretty big revision which was specifically designed for rigid pavements. So what you can see is, starting in 1961, it was called the Interim Guide for Design of Flexible Pavement Structures. So there was not even much consideration of rigid pavements in the 1961 standard. By the 1981 revision to the standard, a large section on rigid pavements had been added. So the design of rigid pavements started off slowly, but then it picked up quite significantly, such that more additions had to be added just to accommodate knowledge about rigid pavements. In 1986, 1993 in particular, and 1998, very significant revisions were made by this point. And by this point, AASHTO had been renamed to AASHTO. So the AASHTO guide for the design of pavements, this was no longer flexible pavements. It was understood by then that you had both flexible and rigid pavements. So by 1986 came the AASHTO guide for the design of pavements. This is a very, very celebrated guide. This guide to this day is actually used very widely around the world, even though in the US and even in India, this system of this philosophy of the guide, which is an empirical philosophy, that has largely been dropped. But to this day, it's used widely around the world. In particular, the AASHTO 1993 guide, which I've highlighted here, this was probably the most celebrated guide in history of pavement engineering. The 1993 guide, first of all, still used a lot of data from the AASHTO road test, but a lot of more data from live test sections, from active roads, was collected. Those related to performance, those related to uncertainty. So we had the AASHTO road test, and after that, a few more smaller road tests, for example, the Min road test, they were conducted and to an extent are still being conducted. But a lot of data was also supplemented by monitoring active roadways and then supplementing data from the AASHTO road test into these active roadways. So the 1993 design guide and a minor revision which came in 1998. By the way, that 1998 revision, again harking back to what happened in the original guide, was also largely for rigid pavements. Quite a lot of information, particularly on uncertainty and joint design, was added to rigid pavements. So by 1998, we were basically at the very best in terms of the design of rigid pavements. Now, what changed significantly is 1998 to 2004 in the US, another project was initiated. Now, this was a particular program they have in the US, which is called the National Cooperative Highway Research Program. They had a particular project which was called Project 137A. And what came out of the official name of the project was Guide for Design of New and Rehabilitated Pavement Structures. So by this point in the US, they actually had gone to a point where they were not designing a lot of new roads. They had a very large road network. Now it was a question of designing a couple of new roads, but also rehabilitating existing roads to extend their service life. So this project, again, it consists for both flexible and rigid pavements. This was from 1998 to 2004. This project was basically mechanistic empirical design. The aim of this research project was to develop a completely new philosophy of pavement design, moving away from the empirical design. So this 1993 and 1998 designs, they were purely empirical designs. They were largely based on some testing and some statistical models built on those tests. They were not based on any physics or mechanics. This project, NCHRP 137A, was tasked with coming up with a completely new philosophy of design and a new code of practice of design based on that. That code of practice, which was launched in 2008 formally, became the AASHTO Mechanistic Empirical Pavement Design Guide, or MEPDG. And along with it, in 2011, they also released a companion software. The reason it's a companion software is because, as we saw, modern mechanistic empirical design using the finite element method is quite sophisticated. It's quite complicated. It's not something you can do by hand anymore. So the old 1993, 1998 design guide, people would set up spreadsheets. They would spread up Excel files and do the calculations over there. By the time we came to the mechanistic empirical pavement design guide, it was essentially impossible to do that anymore. So in 2011, a companion software, which was called the AASHTO Pavement ME design software, this companion software which implemented the design guide, was also published. It cost quite a lot, this companion software, but it was really a major change in the way design was done, because it moved away from empirical design into mechanistic empirical design. And understanding that ME design is pretty computationally intensive, it also generated this companion software, which is now used very widely in the US in particular. You'll also find it used in many other parts of the world. So here is just a little screenshot of the companion software. This is a slightly older version. They've actually updated the interface a little bit, but what you basically have is you can basically set some traffic information, you can set some information about material properties, you provide some default values. We'll talk about these values a little bit, and it's going to come up and tell you what is the suitable design. If you have a given amount of traffic, if you have a certain type of climate, if you have some choice of material properties, what is a suitable and an appropriate design for the rigid pavement. So the nice thing about having this companion software is you don't really have to know the ins and the outs. As we progress in the next couple of lectures talking about AASHTO Pavement ME or AASHTO MEPDG, I will actually take you through many internal aspects of how these calculations are done. I think you will, well, take my word for it, but you will agree with me by the time we finish. It is quite sophisticated. There are a lot of details. Actually setting up a spreadsheet to do this would be very difficult. So the nice thing about having this software is a very large amount of sophisticated details are directly incorporated into the software. So you as a user do not have to understand a lot of these details. Instead, you just follow along. The software will tell you exactly what inputs to provide. Follow along, provide the inputs, it will perform the analysis for you. It's a pretty, by its standard in 2008, 2011, it was a pretty radical new way to do design. Okay, so what was the need for doing this? As I showed you in 1998, a very sophisticated design code, which is the AASHTO MEP, the AASHTO 1998 design code, empirical design code. It was pretty sophisticated. A very sophisticated design code has come up. What was the need for this new project and this completely new way of designing rigid pavements? For that, we have to actually think about some of the shortcomings of the approach of the AASHTO road test. That is, what are the shortcomings of a purely empirical method? So first of all, it was difficult and expensive. As I said, you had to get land. On that land, you had to construct these road sections, these test sections. And then you had to bring traffic, these heavy trucks, which were loaded up with bricks and other materials, but they were loaded up. And then for 4 years, non-stop, continuously, you had to drive these trucks on them. That is very expensive to do. So these type of road test approaches where you conduct focused experiments for several years, these are very difficult and expensive to do. You also have a limited combination of pavement structures and materials. The number of different types of rigid pavement materials that we have today, well, there are different types of cements also, but then we also have different types of what are called supplementary cementitious materials, fly ash, silica fume, etc. And different varieties of combinations for aggregates, for example. So we have virgin aggregates, we have recycled aggregates, we might have some byproduct aggregates, etc. The variety of combinations that we have today in terms of materials for rigid pavements is so high that it is basically impossible to check all of them within a given road section. So you could only check a limited combination of pavement structures and materials in these test sections. There was a significant change in traffic type and volume over time, as many of you have probably experienced in your lifetime. Even in India, maybe a couple of decades ago, there was not that much traffic. Today, the amount of traffic in our cities has increased spectacularly. But actually, it's not just the volume of traffic, it's the nature of the traffic. Trucks have become heavier. More trucks are traveling. Trucks are carrying heavier goods. The configuration of axles on trucks has also increased. And lastly, and all of these things could not have been taken into account during the AASHTO road test. That means if you wanted to stick to the philosophy of the AASHTO road test, which is the empirical philosophy, then every 10 years or so, we have to keep conducting these very expensive experiments and completely reanalyzing the data and coming up with brand new design codes. It's not feasible. And the last shortcoming of the AASHTO road test was, as I had mentioned earlier, very limited consideration of climate and subgrade conditions. Subgrade conditions here mainly refers to moisture conditions. So the amount of moisture in the subgrade, which has a very strong effect on the strength of the subgrade, on the properties of the subgrade. So there was very little consideration. As I mentioned, this Ottawa, Illinois is a very small place. It's a very cold place. It does not even represent all the climate conditions in the US. Forget about representing climate conditions around the world. So the approach of the road test is you don't, if you want to use road tests to create design guides or design codes, not only do you have to keep doing them every 10 years, you have to do them in every representative climate location within a country, and then similarly with across all countries. I think you will agree with me at this point, it's absolutely not feasible. It was a very excellent amount of work which was done in the 1950s and the 60s. It's not really something you can reproduce in a large scale. There are still some road tests going on, by the way, but it's very difficult to keep doing this and trying to develop new design guides out of it. It was really these shortcomings by the dawn of the new millennium. It was these shortcomings that led to the need for a completely new approach. It was not just the need for a new design guide, but for a completely new way to create these design guides and to analyze and design rigid pavements altogether. That was the mechanistic empirical approach. So Pavement ME, as I said, MEPDG, Pavement ME, I'm sort of using these two terms interchangeably. So Pavement ME overcame these issues through two approaches. One was the mechanistic approach. So as I said, one issue with using the empirical approach is if your load changes, if your material changes, if your structure, that's the thickness of different materials, if your or different layers and the materials in those layers, if your pavement structure changes, if your climate changes, then you have to conduct a brand new road test. The advantage of using mechanistic approaches, we are using a physics-based model, that is solid mechanics. We use physics to model a variety of these cases. So these structures, materials, loads, climate, etc. Instead of empirically analyzing and running each of them, we use fundamental physics. Now, I should say, when we use fundamental physics, I'm not saying we don't need any experiments. For example, what we discussed previously in the previous modules, Young's modulus, for example. Well, if you have a brand new material, of course you have to measure the Young's modulus, you have to measure the Poisson ratio, you have to measure the flexural strength, etc. Those are what we call lab scale experiments. They are not difficult to conduct. Most universities do have the machine instruments to be able to conduct those tests, so it's not particularly difficult. So in these mechanistic approach doesn't mean you've abandoned experiments. It means you don't need large scale expensive experiments. You can work fine with small lab scale experiments. So the mechanistic approach could then eliminate the need to keep performing road tests. Instead, you can perform a few small lab tests and develop these physics-based models. The physics-based models will get you up to the point of calculating fatigue damage. And then the second approach was developing these transfer functions, which is empirical functions which take you from fatigue damage to distress. These are developed by observing in-service pavements. You do not have to construct a special test section. You do not have to keep running traffic day and night on them. Take any existing road, monitor the traffic, monitor the climate, monitor the kind of distresses developed, perhaps monitor the stresses which are developed, and you can use that data to develop transfer functions. This is not expensive. It's just a little bit of instrumentation. It's a little bit of work. It is nothing nearly as difficult as constructing these test sections. So the mechanistic empirical approach, first and foremost, is a practical approach. It's an approach which allows you to actually create new data, to collect data at a reasonable pace, and to consider a wide variety of variables fundamentally through physics-based models, instead of having to conduct brand new tests every time you had some changes in, for example, material properties, pavement structures, etc. And perhaps the most important aspect, which is a little more subtle, but it comes out once you do the process, perhaps the most important aspect of mechanistic empirical design is that it provides a scientific basis to understand why a failure occurred. So, for example, if we went by the empirical approach, we designed the pavement and the pavement developed premature cracking, or it developed a lot of cracking much earlier than was expected. We don't know why. Of course, it could be that certain variables were measured wrong, it could be certain traffic was measured wrong, but because we're using an empirical approach, we don't actually know what was the exact problem that caused the section to fail. All we know is that the design was not correct. That's an issue with empirical approaches. You don't have explainability in the empirical approaches. In the mechanistic empirical approach, not 100%, but to a large extent, we do have a scientific basis where we can go back and understand why a particular failure occurred. It could be, for example, the subgrade had a lot of moisture, and because the properties of the subgrade and the moisture condition of subgrade is explicitly considered as part of the design, we can actually model the pavement with, say, moisture having a high subgrade having a high amount of moisture, and see whether the observed premature cracking could also be captured using these models, which then tells you why exactly the premature cracking happened. So mechanistic empirical design gives us a scientific basis to understand why a failure occurred, so that in the future we can improve upon our design methods. So there are this little graphic which I have over here tries to give you an overview of the different ways by which the pavement AASHTO pavement ME works. That is, it went from the AASHTO road test to the design guide. And in that process, what changes happened is the AASHTO road test, as I said, considered a limited number of structures. Using the pavement ME, you can consider a very wide variety of designs, because fundamental physics is going to come to our aid in order to analyze those designs. In the AASHTO road test, the amount of traffic at that time when it was constructed in the US was around 1.1 million repetitions. Today, easily you have over 50 million repetitions. The climate consideration in the AASHTO road test was for a couple of years. So it was a one location for a few years. Whereas now we are able to consider a wide variety of climates over a very long period of time, because we're fundamentally using physics to consider climate. And finally, back in the AASHTO road test, they could only consider really one small set of materials, whereas now new and diverse materials can be considered. So these are really the advantages of moving from the old AASHTO empirical guide to moving to mechanistic empirical design guide. And by the way, as we'll talk about a couple of lectures later, in India also around the 2010s roughly, we also moved from a purely empirical approach, largely based on the AASHTO road test and some experiences within India, to a new mechanistic empirical approach. So all these advantages which I'm giving for the MEPDG or the pavement ME also apply equally for the Indian experience. Okay, now a little bit, I just want to talk for a minute on analysis versus design. Module 2 and Module 3 was based on analysis. What do you do in analysis? In analysis, you're given a pavement structure. You're given the materials, the properties of the materials. You're given the loads. You're given your climate-related inputs. You're given some information about variability. You are asked to calculate performance. Performance basically means stress or distress. So you're given a lot of inputs. You're asked to do some simple or some complicated analysis to come out and calculate performance. Design is the inverse problem. In design, we are given almost nothing. There is no road. So because there's no road, there's no pavement structure to give. There are no materials. There's no road. We don't know what traffic is on the road, and therefore there are no loads either. There's no road. We don't know where the road is, so we don't know what sort of climate inputs are there. We certainly don't know anything about variability. Out of all that, we are not actually asked to calculate stresses or distresses in design. We are asked to design a road that meets some desired performance. Now, that desired performance could be a maximum stress. That's actually now not how it's done. Or it could be some maximum amount of distress. So you could say a certain number of slabs cracked for every for an intersection, a certain amount of faulting, a certain crack width, etc. So in analysis, we are basically given a large number of inputs. We don't have any performance or any target performance as such. So we really want to calculate what is the performance. We don't really have a target in mind. We just calculate a value and that's what we get. In design, we are given absolutely nothing. We know nothing, etc. Which, by the way, when I say we know nothing, that basically means we have to figure out ways to calculate these, or actually at least estimate these. We don't know none of these. All we know is that finally whatever comes out of the design should meet some targeted performance. So from this slide here, you can see that analysis and design are two very different beasts, and they have to be handled quite differently. This is how broadly, and we'll go into more details in subsequent lectures on this, this is how the MEPDG actually handles design. That is, it takes certain inputs. It goes through some variety of models. I'm not going to detail what all the models are, but it makes an assumption of the structure. It goes through some variety of models which are about traffic, it's about structural models, about climatic models. We'll see this in subsequent lectures. It gives out some kind of a pavement response. That is, the pavement response is stress, strain, and deflections. And then it uses a transfer function to calculate some type of a distress. That's, if it's flexible pavements, it could be fatigue and rutting, or for rigid pavements, it's cracking, it's faulting, etc. some reliability is added to it, and then we check, is it satisfactory? If it's not satisfactory, go back, change your analysis, change your structure, and then redo the analysis until the distresses are below some acceptable threshold, which then we call the final design. So this is the overall procedure that we use in Pavement ME. Now, one question to ask is, if we know nothing about the road, how do we even begin to do a design? As I mentioned over here, you have to do a bunch of calculations, structural climate calculations. But if we know nothing about the road, how do we even do these calculations? Okay, one option could be, let's go out and collect all the data required for any input. Let's do our detailed mix designs. Let's do a traffic survey or predict some type of traffic. Let's collect detailed information about climate for the exact location where the road is going to be constructed. That's an option. The other option is, let's assume some typical values. Of course, those typical values have to be related to a reasonable design. So we come with some reasonable typical values and come up with a design. We can update the values later, but we start with some reasonable assumptions. These reasonable assumptions of typical values is really a very important factor in mechanistic empirical design. So typically option 2 is what's used. We don't do a lot, when coming up with designs, we don't do a lot of detailed calculations in the beginning. We come up with a number of assumptions. We correct the assumptions on the way. So Pavement ME follows a similar philosophy where you have 3 levels of design. Level 1 is where you collect detailed project specific data. So you might do all your geotechnical work, you might do all your mix design, you might do your traffic modeling, etc. right in the beginning before doing any pavement design. Level 2 is where you have some correlation with some limited testing. So you don't go out and measure all the properties of the soil. You might do, for example, an SPT test or some DCP test or something of that sort, and then calculate values which you're interested in later. Or you could do a level 3 analysis, which is where you use a typical value. Let me illustrate this. So this slide is basically going into a little more detail on level 1, level 2, and level 3. But I think it's better if I illustrate it with an example. Young's modulus we have seen regularly in our analysis section. So how would level 1, 2, and 3 fit in with Young's modulus? Level 1 would be you design your actual mix design that you want, so you know exactly what are the different components, make some trial batches, and conduct the tensile tension test to measure the Young's modulus for a certain number of replicates. So that's properly you do your design and you conduct a lab test. Another could be, suppose we know that the road we're targeting is M40. That is, we're saying the compressive strength, the characteristic compressive strength, FCK, is 40 MPa. And then you use some correlation. We saw what those correlations were. It's related to the square root of FCK. So you use some correlations to calculate what a modulus would be. That would be level 2. That we at least know the strength and we don't directly conduct a test for elastic modulus or Young's modulus. We use a simple correlation instead. Level 3, which is actually what we've been doing in several examples, 30 gigapascals. So it's a reasonable value, assume a reasonable value and move forward. It will be corrected later during the design process. So level 3 in practice is what is used very widely in design, both in mechanistic empirical pavement design in the US, that is AASHTO Pavement ME, as well as in India. Okay. Lastly, the AASHTO Pavement ME follows an incremental damage model. Now, previously in empirical design, we don't do damage modeling. We have a set of inputs and we get the thickness in the end. But in mechanistic empirical design, the analysis is actually done at an hourly level. So all the inputs that we need is actually needed at every hour. So the hourly climate data, monthly traffic, which then is converted into some hourly factor, although little more details on this will come into a few lectures later. We have to determine the hourly stresses and fatigue damage. And then from there, we have to calculate cumulative hourly and later monthly stresses, cracking, faulting, IRI, etc. So we follow this incremental damage approach where we have to do the analysis incrementally for every hour or every month of the analysis, as opposed to a one-shot approach, which we would use in an empirical design method. Here is an example of an incremental approach. So over here is pavement age in months. Here is IRI smoothness. It's some type of distress. So what AASHTO ME does is it will actually calculate for every month of the analysis period. It will calculate what is the smoothness of the IRI and make sure that it is below some design limit. So in this case, it seems here after 250 months, that's quite a lot actually, so more than 20 years. After 250 months, the IRI reaches a certain design limit. So you'll see these kind of outputs coming in when you use Pavement ME. Okay, so with that, we can conclude that pavement ME is a new and sophisticated way. Well, it's 20 years old, but it's a very, very sophisticated way. It is very different philosophically from previous design methods, which were purely empirical in nature. It does, however, come with a lot of intricacies, a lot of details, a lot of things we have to know about. So in subsequent lectures, we're going to talk about several of these details, a little ins and outs of how to do these calculations in AASHTO ME, and then we'll move on to IRC 58 and see how we do it in Indian practice. So in the next lecture, we'll talk about traffic characterization, which will be the first aspect we have to understand for mechanistic empirical design. Thank you.